Okay, so howdy, my name is Hunter Spear.
Howdy, I'm Andre Leon.
Howdy. Oh, howdy, I'm Gabriel Avery.
This is our final project for MXDT 375.
Here's our overview. This is the steam shovel that's used at the beginning of the Industrial Revolution for construction purposes. As you can see, it has three main components: a beam, the shovel itself, and the motor. And it's all connected with one single cable to action the shovel to pick up any cargo it may have.
So the steam shovel is going to have a fixed arm, and on that fixed arm is going to have a pivot where the shovel arm is going to be connecting. And the way that the shovel arm is going to be actuated is the motor, which is connected to the base arm, is going to have a string round around the spinning spool, which is then dropped over the base arm and then tied off to the bucket arm, so when the motor will spin, it will raise the bucket arm. And this system is connected by a controlled by a potentiometer, which, depending on the resistance, will control the speed of the motor.
Alright, so we had Gabriel be the one creating our presentation as well as also the computing data, with Andre being the one who did all the simulations with the data that was provided by Hunter, who was the one who combined all the components together, all the wiring in the Arduino, including the debugging with the broken Arduino. Then I was the one who did all the CADing and made all the 3D parts to go with this thing.
Gabe.
So our timeline is we gave our proposal earlier this month, and then on 4.7 we have the electrical system mockup complete. 4.15 the first prototype was complete. 4.21 the second prototype was complete, and then our final submission, which is the 3rd of May.
Our expected outcome here was that the potentiometer had a direction and speed control, that the Arduino was able to read the resistance of the potentiometer, and that the potentiometer position determined the PWM frequency and the signal. Also that the motor winds and unwinds a rope connected to the bucket so that it will get up and down and shovel any dirt it might have, and also that the motor encoders were used to measure the position.
Awesome. So this is the electrical design schematic. Biggest thing was we had our motor controller and our Adafruit hooked up. Our Adafruit is being read through the Arduino using the SCA or SCL and SDA wires, using the I2C program. And so we had our voltage going to the motor spliced into the Adafruit so they can read the current and voltage. And then we have the actual potentiometer as our user control, and depending on the position of the potentiometer, it will give a signal read by the Arduino that is then interpreted into the direction signal for the motor controller and the pulse width modulation that goes into the enable pin. And then the motor controller also is ideally giving the Arduino Nano the encoder positions so that we can calculate where the motor is moving. So here is final assembly. We have power sensor on the board with the Arduino, and then the motor controller is wired up with the motor as it's intended to be. potentiometer is out here, it has wires connected to power and ground, and then the middle post goes to the reed. And then you can see here the actual physical mechanism with the, we're looking at the top, but we can see the motor, the arm, and then the moving arm is a little bit obscure right now.
So here we can see the actual Simulink diagram. As you can see, we have a voltage source that represents the voltage that's given to the motor. Here the voltage is connected to the ground, the function, and it's got several sensors to determine what it has. And it's connected all to the DC voltage source, which is actually the motor that transfers the electrical energy into mechanical energy. And this one is connected to the system itself, which consists of a damper, a mechanical rotational reference, and an inertia. These elements are all intertwined to make the system, also known as the actual arm itself.
So here is our data for a data set where the arm was in the lowering position. As you see, over time, the position data goes from around the 425 to 0. And you can see that although the voltage and amperage graphs are kind of erratic, you can see that they have an inverse relationship, which is something that you would expect to actually get. So next slide. And this is our data for raising. You can see over time that there is a large spike in our amperage, and that is when the most amount of torque is required to raise the arm. And that spike is correlated with the arm beginning to move, and then there is an overall baseline voltage that stayed pretty constant.
And here is a demo video. We had an incredibly frustrating set of setbacks with the hardware. When we were initially given the hardware kit, our Arduino was not functioning. The motor encoder was not functioning. The speed controller was not functioning. And so we asked for a new kit. And now with that new kit, we are still having significant issues. I'm able to get the program to work on other computers or Arduinos, but I'm not able to put it all together with these pieces. So for this demo video, we manipulated the system by hand in order to show what the system should do. And here are video links to our proposal video that we made earlier this semester and our demo video. And then of course this video that we're recording right now, you already have a link for. So thank you so much for watching our video, and have a great day.